All right, welcome to lesson 2 of our 4th unit, permutations of different objects. So we're throwing a new word in there right off the hop. So lesson 1 was all about the fundamental counting principle, and we're going to start with that, but we're going to see kind of how that changes into a formulaic way of thinking and a way of being able to calculate options and different ways to arrange things without having to write out all those blanks and fill in all those possible spaces. So when you're dealing with permutations, you are still able to use the fundamental counting principle, but I'm going to show you a formula and you're going to have to find on your calculator. There should be a button that you will use, and I'll have a separate video kind of showing you where that button might be and what it might look like. So if you want to pause this video and at any point and watch that next video on calculator buttons, it's not very exciting, but it will get the job done. And these are some funny looking buttons, so you might want to check that out. So do that at any point. But we'll dive right in. And the key thing to know, oh dear, is how not to scroll down to the bottom of your video page. No, the key thing to know is that we are going to look at permutations. So this lesson and lesson 3 look exclusively at permutations, and the key things to note about them are that they're an arrangement of a set of objects where the order of objects affects the total number of arrangements. In other words, order matters. Very, very, very important piece of information. Okay, so permutations, order matters. Okay, and lock that away because once we hit lesson 4, it becomes important that we make that distinguished kind of characteristic very obvious. So using what we learned in lesson 1, we can answer example 1 without this idea of permutations coming into play. But we see that it is a permutation because the order of letters that we are rearranging in this example, M-A-T-H, changes the number of options. We would never say that M-A-T-H is the same thing as A-H-M-T. Those are completely different things. Now remember from last video, these are both called words in math for our purposes. Don't talk to your English teacher and show them this and say, well, that's a word. Yeah, no. But for us in math, for this unit, AHMT is a word. Okay, so the order does matter because those are two different things. One actually has meaning even if you said it to your English teacher. The other one would not have any meaning if you tried to pronounce that to anyone at all. And I'm not going to. So order matters. We have 4 letters and they can be arranged in any way. So 4, 4, 4, 4. But given the distinction here, how many ways can the letters of the word math be arranged? I might not think that that's the right way to do it. I might say I've got 4 options for this first letter, but only 3 options for the second letter because I've already used up one. So if I use A here, then I only have 3 letters to choose from in my next spot, M, T, or H. So say I choose H. That leaves me with only M and T to choose from here. So it's only 2 options. If I choose an M here, then I've only got 1 letter left. So I have to use it, and that has to be T. Again, this is still using our fundamental counting principle. I would still multiply these options together. So 4 times 3 is 12, times 2 is 24 arrangements. Okay, so again, whereas in lesson 1, if we go back, we're not told a lot of the time that we are allowed to have things repeating. And so in that case, we were allowed to choose the letters repeatedly. So F, 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 F for this one is kind of what we did. If we went back and started restricting things, it would change if we weren't allowed repeaters. And so that's what we're seeing here. So we're adding that restriction. Okay. Again, if we didn't add that restriction, then I'd have 4 options here. I could choose M, 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 and M, but I'd have 4 options for all 4 blanks. In which case, that would give me 4 times 4 times 4 times 4, which I'll have to use a calculator for. That's 256. So we see in this example that one little restriction, which seems pretty insignificant, made a significant difference in how many arrangements I have to work with. So that lack of repetition is really, really important. So again, because I'm arranging all of these letters, I'm going to work with the assumption that I can't have to restrict my options. So counted has 1, 2, 3, 4, 5, 6, 7 letters, and I'm using all of them. So I've got 1, 2, 3, 4, 5, 6, 7. To start with, I have 7 options. I could choose any of the letters. So I've got 7 options. But then I used that letter, so it's going to be any of those number letters minus the used one. So that means I only have 6 to choose from. But then it's going to be any of the letters minus both of the used ones. So that's 5. 4, 3, 2, 1. And I'd multiply them together. So again, implying all letters need to be used. Creates a restriction. Okay, and I would do this by punching it into my calculator. So on my calculator, I'd go 7 times 6 times 5 times 3 times 2 times 1. Now, you might type in the times 1 or not. That's completely up to you in order to get 50, 40. Different arrangements. Now, I am very grateful for the fundamental counting principle because I would not want to sit and have to write out all 5,040 possible arrangements in order to know that that's how many arrangements I could have. But typing in 7 times 6 times 5 times 4 times 3 times 2 times 1 is tedious and takes time, and in math, we like to be efficient as much as we possibly can. In spite of the fact that we have an hour and a half spent on lesson 2 in unit 3. Sorry about that again. So factorial notation can be used to simplify this calculation. This is where math gets exciting because we literally start using exclamation marks. So factorial notation looks like this. Yay! So factorial signs mean to take the product of all natural numbers. This means positive whole numbers. Greater than 0. Is another way of thinking about it. And so in general, we can say that if any number is excited in math and has a factorial sign, what you're doing is you're taking that number times 1 less than it, times 2 less than it, times 3 less than it, all the way down to 1. do not include 0. Okay, so that being said, the definition of the factorial of 0 is 1, because you need a root to start with. Just like anything to the power of 0 is 1. Kind of in the same vein, using the same philosophy, that we need that seed to start it off. So on your calculator, you might have an exclamation button. If you don't, it might be a second function button. If you don't have that, then you might need to find a different button that has something to do with like probability. Might say PRB. Again, I'm gonna, if you want to pause right now and flip over to the video on how to find this button on your calculator, go right ahead, do that now. But what it means is that you're just going to punch it, the definition of it is that 7 exclamation mark, or 7 factorial is how we would read this now, is 7 times 6 times 5 times 4 times 3 times 2 times 1. But I don't want to write that out. I don't want to type it into my calculator, so I'm going to find that button, and I'm going to punch it in. Now, if I look on my computer calculator, I see that I do not have it, so I'm going to have to keep typing it in this way. So I'm going to have to use my own personal calculator in order to do this. Oh, no, never mind. It's right there. Yay. So if I put 7 factorial, I get 50/40, just like that previous example. Okay, so 3 factorial, I know that one because it's nice and easy. It's 3 times 2 times 1, which is 6. Don't get excited and write an exclamation mark at the end. That is bad. Don't do that. Okay. Instead, we're going to keep working. 12 factorial. So again, 12 times 11 times 10, all the way down to 2 times 1. Okay, and I'm not even going to write it out because that's just not efficient. And then I go into my calculator, I'm not going to type all those individual numbers in. I'm going to hit my factorial button and see that it's this monstrous number. Four, 7, 9, 0, 0, 1, 6, 0, 0. Okay. -2 factorial. Now this is where it gets a little weird. So I'm going to do it on my calculator first so you can see kind of what happens. If I go negative, oops, -2, and then factorial that, it will tell me that I can't. And why can't I? Well, because I'm starting in the negatives, and factorials can only deal with positive numbers. So this is not possible because it can't go past 1. It can't go into the negatives. It doesn't even really include 0. 0 equals 1. 1 equals 1. That's another weird discrepancy, so just bear that in mind. Okay, so no negatives, if you need to remind yourself. Because it's not going to count upwards to 0, that's not a thing. It must be positive. Okay, again, 0 equals 1, 1 equals 1. Now this is a funny example. I could just punch this into my calculator. But I could also not, and it wouldn't be as big of a pain in the butt as this first one. And the reason is that I can break it down into 8 times 7 times 6 And I'm going to write this one all out for a very specific reason, so bear with me. All over 6 times 5 times 4, 2, 1. Okay, but what happens here is 6's cancel, 5's cancel, 4's, 3's, 2's, 1's. So instead of writing it all out like that, because I am going to be my efficient self, is I would have actually written it out as 8 times 7 times 6 factorial, because 6, 5, 4, 3, 2, 1 is 6 factorial, divided by, and I would have left the denominator like that, and all of a sudden, bang, I can cancel all of that out, and I just have to do 8 times 7, which is 56. Okay, so even though it looks like a monstrous type of question, because of the fact that we are dividing by 6 factorial, which is less than 8 factorial, I can break it down and simplify it like this. Okay, so I can do this by mental math. Which means that all of a sudden this question becomes something that it can be on the calculator section, or on the non-calculator section. This last piece, I can do the same idea. Now, I know you're like, but Ms. Conrad, I'm not allowed negatives. N minus 1 doesn't have to be negative. N could be a number that's bigger than 1. All of a sudden, I've got options. So I'm going to break it down to n plus 1. Well, my next term is going to be n plus 1 minus 1. So I'm just going to write that up here because I know that those cancel out. So this next term is just n, and then the next term is 1 less than that. And I'm going to stop here because all of a sudden I'm seeing the same kind of, not problem, but simplifying opportunity as in the previous one, because now I've created a place where my denominator is showing up in my numerator, which allows me to cancel. And thus, I just have n times n plus 1, or n squared plus n if I FOIL it through. And again, these are both totally fair questions on the non-calculator section. Whereas if you were asked this question, I would expect that to be like a multiple choice question on your calculator section, if they even ask something as simple as that at all. But I wouldn't even anticipate that kind of question on the provincial exam. Maybe as a gift. Okay, so how do we use the factorial? Because it's all lovely that it does this great thing where it multiplies descending numbers all the way down to 1. But why do we care? Well, we saw it in the first 2 examples why we care. But we can see it in these following examples as well. So example 4, a puzzle designer decides to scramble the letters in the word education. So again, scramble is going to be a nice word for you because that means that all letters are in play and must be used. Okay, so there's no option to go 9, 9, 9, 9, etc. Okay, we're not doing that. And they're creating a jumble puzzle. How many 9-letter permutations of education can be created? So again, it's a permutation because order matters, because education and an indicator are 2 very different words. So order matters. Which letter goes where matters. So what I can do is a couple different things. Look at how to use factorials in this particular one. So originally I would have put 9 lines here, and 9, 8, 7, 6, 5, all the way down to 1. But because I have now learned about this exciting new math, factorials, I'm going to use that, and I know I'm going to say that this is 9 factorial. And then I'm just going to use my calculator. There we go. That's how many different 9-letter permutations can be created. Okay. In example 5, we're looking at 6-letter permutations of A, B, C, D, E, F. And again, because we're talking about permutations, we can assume that we are using all letters. Okay. As we get farther into this unit, that will explicitly have to be spelled out for you more. But in this case, A, B, C, D, E, F, we've got A, B, C, D, E, F. We've got A, B, C, D, F, E. Those are different arrangements, so again, order matters. It is a permutation. And generic permutations, let us just straight up use our factorial option, which is 7. Nope, not 7. 6 factorial. So again, that's 6 times 5 times 4 times 3 times 2 times 1. But find that button on your calculator and you'll quickly get the answer of 120. And so there we go. That's all we have to do. As long as it's descending and everything gets used up, we can use factorial. So those are our 2 stipulations. If order matters, everything gets used. And the last stipulation is that there's no repeaters. So you'll notice in all the words that we've seen so far, education, and if we go up here and we look at continue or counted or math, we only have each letter showing up once. Okay, so that's really important to note. So if all the objects are not chosen to be arranged, then we need to start using a different formula because we're no longer going all the way down to 1. So instead, we use the permutation formula. And so it's a little weird looking, okay? So this is what it looks like in all its beautiful glory, okay? This last piece on the end here is just strictly a restriction. That's there so that our denominator can't be 0. Right? And it also can't be negative because we're not allowed to take factorials of negatives. So what happens here is that the little n, oops, deleted all my beautiful highlighting. The little n here is how many options you have. Objects or options. The little r is representing the objects actually being chosen. So what does that mean? Well, if I was to read this and put it in words, I would say that this is, and a way to kind of help me like kind of read it is I would read it as 5 pick for a permutation 3. And how I use this formula then is that I would go 5 factorial over 5 minus 3 factorial. Okay, so subtracting what I'm actually using from the total number of options that I had to choose from. From here, I would say, okay, well, 5 minus 3 is 2, so 5 times 4 times 3 times 2 factorial over 2 factorial. Again, using that strategy that we saw way up here now, where I tried to get to a factorial that can cancel out with my denominator. So I do that, cancel them out, and all of a sudden I've got a manageable 5 times 4, which is 20, times 3 is 60. So I'd have 60 options if I had 5 things to choose from. So I had 5 students, but only 3 get to be the president, vice president, and treasurer of student council. That would be an example where we would see this kind of situation. Okay, and this next one, again, it would be 8 options to choose from, permutation, and 4 things are actually getting selected. So there might be 8 paths to take home, but I'm only going to go one. I'm only looking for 4 different ways to get there. That's not the best example because the order doesn't matter then. But kind of. You'll see some examples where we're choosing paths later, and you'll see what I mean. Okay, so 8 pick 4 is another option. We would do 8 over 8 minus 4. I would simplify this. And again, this is really bad math notation. I'm sorry that there's not enough space to work vertically. You should never have running equal signs. 8, 7, 6, 5, 4 factorial over 4 factorial. Cancel those guys out. And then calculate 8 times 7 times 6 times 5. Which is 1, 6, 8, 0, 1,680 different options. If I go 7 over 7 minus 1 factorial, which would give me 7 times 6 factorial over 6 factorial. Those go away. I just have 7 options. So if you're just choosing one thing and there's 7 things to choose from, you can only choose one of those 7 things. So you've got 7 options, which is kind of nice. And 6, and we're picking 0. We've got 6 factorial over 6 minus 0 factorial, which we could rewrite as 6 factorial over 6 factorial. And anything divided by itself is 1, which is essentially what we've been doing every time we've canceled out, just reducing it down to 1. So that would be my last one. So again, when we are making no decisions, there is only one option: to make no decisions. Okay, so we've got example 7. 8 students are competing in a 200-meter race. How many ways can the students finish first, second, and third? So in this case, order matters. I care if I'm finishing in first, second, or third. It's not enough to finish top 3. I want to know which place I'm in. And for that reason, we're using permutations because it matters. Maybe if you're not as competitive and you're just happy to finish the race, then you're in a good place. But I don't know about you, but I'm very competitive. So first versus second, that's different. Second is first loser. No, I'm just kidding, but only kind of. Okay, so 8 students are competing in a 200-meter race. So I have 8 options to choose from, but there are only 3 places to land, so not all 8 of them are going to get used. So this is my permutation and how I'm going to write it. If I go to use my formula, I've got 8 minus 3 factorial, so I'm going to go 8, 7, 6, 5 over 5 factorial, and that leaves me with 8 times 7 times 6. Which is 2016, if I'm not mistaken. Yes. Okay, so this is how I would use the formula to do this. You might actually have a button on your calculator that lets you type in this exact thing and evaluate it, and it'll do all this math for you. Again, if you want to pause this video at this point and go to the calculator video and see what that might look like on your calculator, do that now, but make sure you come back and finish this lesson. So we've got a couple more examples. So example 8 is looking at, of 12 songs on your all-time favorite list, how many ways can you listen to 4 of them? Okay, and so listening to them in order of like 1, 2, 3, 4 is different than listening like your top 4 picks versus listening to like your 8th, then your 3rd, then your 5th, then your 7th. Like if you bounce around on that list, the order matters because it changes the playlist. Some songs just flow better into other songs, and so order matters here too. So we would still use permutations, and so we've got 12 songs to choose from, but I'm only picking 4. And again, I can use my calculator to pump this out, but just in case, I've got 12 over 12 minus 4, which is 12, 11, 10, 9, 8 factorial over 8 factorial. And that's going to get me some large number, specifically 11,880 different ways. Okay, now our last question is a little bit trickier. So up to this point, we've been doing word problems, and we've seen the formula, but now we actually need to kind of manipulate the formula. In this case, we are solving for n. So I'm going to have to use my formula here. But instead of writing it on the right-hand side like I have been up to this point, I'm going to set this side equal to it so I can actually like solve for n. So what's going to happen is that I don't know what n is, but I know my r value. So I can fill in as much of my formula as possible. N minus 2 equals 56. And so again, I can break this down just like I have been in these previous examples where I've like written out my numerator until my factorials will cancel. I'm going to do the same thing here. So I've got n times n minus 1 times n minus 2 factorial all over n minus 2 factorial equals 56. And again, that 56 value has to stick around because you can't solve anything if it's not an equation. So don't change it into an expression because then you'll get stuck and you can't isolate n. From here, these guys cancel. That leaves me with n squared minus n equals 56. And welcome back to grade 11 pre-cal. We're working with quadratics again. So we get everything on one side. I'm lucky enough to be able to spot that 56 is the product of 8 and 7. So n minus 8 and n plus 7 would produce this quadratic. And from there, that means that n would equal either positive 8 or negative 7. But we know that we can't have negative 7 choices. That's not a thing. Okay, so no negatives allowed. So 8 is going to have to be my only solution. Okay. In the other part of our example, we're given our n value, but we're missing r. So we'll start the same way. We'll substitute our formula in as much as we can on the left, and we're going to keep that 20 hanging around on the right-hand side. So we've got 5 factorial over 5 minus r factorial equals 20. From here, I'm going to rearrange it to start with so that I can get my variable out of the denominator. So 5 factorial divided by 20 equals 5 minus r factorial. So I know that 5 times 4 is 20, so that's what it would knock out if I were to write this out. This all equals 20. So I would cancel that with my 20 equals 5 minus r factorial. Once I've done that, well, that leaves me with 3 factorial on this side, which means 5 minus r has to equal 3, because I can just I can ignore my factorial signs because they don't actually change the math that I'm doing. So 3 equals 5 minus r, and so r, if I move it around, would be 2. So this one, in my opinion, is a little bit trickier. Solving for r is trickier than solving for n. But if you are a little rusty when it comes to the wonderful world of quadratics, and factoring, you might want to review that. I'll post a couple of videos on that as well for you to go back and just kind of like recap that, although we have seen it in previous lessons in this course. Okay, so I know this was a beefier lesson than the previous one. Lesson 3 won't be quite as extensive, but we were introducing that whole concept of a permutation today and a factorial. So lots of new stuff. There's no practice that goes immediately with this lesson. It's going to show up after lesson 3. So there's 2 sets of practice questions that are going to come for lesson 3. So good news is you're off the hook for homework tonight. Kind of let this all percolate, go over the examples again. You can look at the homework attached to lesson 3 and see if you can do some of them, but watch out for any type of repeater things that are going on, because that's going to be the special case that we look at in our next lesson.